Welcome back to Pragmatic Rust for engineers. In our previous videos, we explored the basics and advanced modeling of the Haber-Bosch process. And today we're taking it a step further.
Indeed, Tim, we're delving deeper with sophisticated analysis and optimization methods to improve our grasp and efficiency of the Haber-Bosch process.
In the first episode of this series, we initiated a simulation of the Haber-Bosch reaction. This was based on a simplified model, and we utilized an ODE solver implemented in Rust.
Correct. And in our second video, we expanded the model to a more detailed version, incorporating complex concepts like inner gases, the exotermination of the reaction, and fugacity coefficients.
I see. And on the Rust programming front, we structured our code into three distinct modules: configuration, simulation, and visualization. This organization allowed us to have the capability to save diagrams directly to our hard drive. However, today's focus shifts to performing live analysis through an interactive web-based tool.
To optimize the Haber-Bosch process, a comprehensive understanding of both design and operational parameters is crucial. Let's start by examining these factors in detail, which directly influence the efficiency and yield of ammonia synthesis.
Great! Let's recap these design parameters first. What are those?
Sure. There is the catalyst type, the number of beds, and the reactor length.
Okay.
All of these are set when the plant is built.
And how does each of those parameters have an effect on the Haber-Bosch plant?
The choice of the catalyst significantly impacts the reaction rate and efficiency. Different catalysts offer varying levels of activity, selectivity, and durability under high temperatures and pressures.
I understand durability. That means like catalyst deactivates and it has to be changed. However, selectivity and activity, what do they mean?
That's right. Activity describes how many moles per second are produced on the surface of the catalyst. And selectivity is more meaningful when you have two competing reactions and want to select the right one.
Thank you for the clarification. What about the number of beds and lengths? In our simulation, we let the solver decide about the needed lengths for the beds. And so for us, it's not really a degree of freedom, right?
The reactor's design, particularly the number of beds, influence the contact time between the reactants and the catalyst, affecting the overall conversion.
Okay.
Each of these beds can have varying length. The length of the reactor plays a critical role in determining the residence time of the reactants, which in turn affects the extent of the reaction.
Well, that makes sense. All of this must be set to build this plant. But what can we change when it is running?
During operation, we can change parameters like temperature and pressure to specific degree.
I see. And temperature and pressure are also highly intercoupled, right?
Yes, and operating temperature is a crucial or critical parameter. Higher temperatures accelerate the reaction rate but can shift the equilibrium unfavorably. Finding the optimal temperature is key to maximize yield. Pressure influences the equilibrium of the reaction. Higher temperatures favored ammonia formation, but they also require more robust and expensive reactor designs.
All right, and what else is there? Like, we have those inner gases in the model, for example.
Yes, but let's focus first on the ones we mentioned first. There are too many other parameters we could analyze.
Yeah, I see. And since it is just an exploratory tool, and we leave a lot open for you, the audience, to add some capabilities. So be encouraged to go deeper into the development of this tool and maybe implement your own parameters and variables and play around with them.
That would be great. By analyzing these parameters, we can determine the optimal conditions for the Haber-Bosch process.
Yeah, however, let's put those optimal conditions in quotes because we're just guessing and not using a mathematical method here that guarantees that we find an optimum. And even if we did, we need to think about the plant model mismatch, which is actually quite hard because, well, we don't own the plant yet. Well, let's now dive deeper into the analysis and see how these parameters interplay in our Rust-based simulation.
So, we have kinetic data for two catalysts. Let's begin by examining the effect when using the Kamer catalyst. We'll maintain our analysis with two beds for now. In this tool, we can adjust the initial temperature of the gas entering the bed as well as the overall pressure in the reactor. Let's set the pressure at 186 bar and increase the temperature in the first bed from 350 to 470 Celsius. Notice how initially the second reactor bed isn't visible. However, as we raise the temperature closer to that of the second bed, it starts to appear in our diagram. With the temperature increase, the reactor's length decreases due to the accelerated reaction in the first bed. We'll aim for an optimal point, say 390 degrees, and then focus on the second bed. For this bed, an initial temperature of 380 Celsius shows a slight improvement in ammonia yield. But let's introduce a third bed at a lower temperature, 360, to shift the equilibrium point further, enhancing ammonia yield even more. This looks quite promising. Okay, team, but I got a question for you. Why don't we use a single bed with the same length as this setup?
I think a single bed, it will be inefficient as the reaction would just ceases when it hits a certain temperature. So the key here is this intercooling to shift the equilibrium point. And our tool, it shows that what theory was predicting. Jonathan, could you summarize the main findings for us?
Certainly. Adding more beds significantly increases ammonia conversion, helping to control the heat from the exothermic reaction. Each extra bed, especially when using indirect cooling, lowers the gas temperature, which promotes greater ammonia production.
Well, but what's the downside?
That's a good question. The downside is that while additional beds boost conversion, they'll also increase operational and capital expenses. We need to strike a sweet point to optimize the efficiency without incurring prohibitive cost.
Mm-hmm. Yeah, and as a reminder, what happens to the syngas that isn't converted in a single pass?
Right. As we discussed in our last video, not all syngas converts in one pass.
Mm-hmm.
The unconverted gas is recycled back into the system.
And to come now back to our temperature selection, which was the focus of our analysis, maybe you can give a one-sentence summary?
Sure. Lower temperatures favor ammonia production but slow down the reaction, while higher temperatures speed up the reaction but reduces the yield.
Good. So we investigated temperature's influence on reaction kinetics and reactor design specifics, meaning the bed length.
Exactly. This is where simulation tools like ours are invaluable, allowing for its virtual experimentation without the risk and the cost of real-world trials.
Perfectly said, Jonathan. Let's compare the two catalyst types in the Haber-Bosch process. First, there was this traditional iron-based catalyst, but what's the second type?
The second is also iron-based, but includes rare elements like ruthenium as promoters. They allowed operation at lower temperatures and pressures. These reduce the operating costs. Let's give a look to this in our tool.
Alright. When added to the analysis tool, you can see new smaller curves at the bottom left, which is great because lower temperature and pressure means less costs. However, what are the drawbacks? Why isn't it widely used, Jonathan?
Yes, the availability and cost of ruthenium are major issues. Only about 35 tons are produced annually compared to 880 million tons of iron. Its scarcity and extraction complexities make it so expensive.
So while ruthenium offers operational advantages and shorter reactors, iron is more economically viable and probably much less risky if you need new materials.
Precisely. Iron dependence and lower costs make it a practical choice, especially considering catalyst replacement needs due to deactivation or poisoning. Now, I wonder how we end up with such a tool. That's not only Rust, is it?
Absolutely, Jonathan. We're advancing from our Rust development showcased in the last two episodes. Let's start by examining our software framework from a wider perspective. As you can observe, our system consists of three primary components: configuration, simulation, and visualization. What we've previously accomplished involves converting our Rust code into executable machine code. This code operates on various operating systems like Windows, Linux or macOS, using a basic terminal for displaying text to users and employing the file system for saving image files. Our goal in today's video is to enhance our tool to accept user inputs and dynamically update the visualization of our plot. To achieve this, we'll utilize WebAssembly as a Rust compilation target instead of traditional machine code. WebAssembly is compatible with all major web browsers. To facilitate this, we'll need some tools to create the needed WebAssembly packages. Additionally, we'll be coding in HTML and plain JavaScript to link our website interfaces with our Rust application and make modifications to our Rust code to enable the interaction with JavaScript. I'm quite confident in saying that Rust is a frontrunner in the WebAssembly domain, thanks to its exceptional safety and efficiency.
Interesting. I always view Rust as a primarily low-level language.
I see, yeah.
However, it appears to be quite effective for web applications too.
That's true. And interestingly, I conducted a survey on my Twitter circle, and Rust is equally used for web application and system programming. If you're curious, take a brief pause to see how my colleague Filippo Tamagini elucidates this unexpected statistics by applying Bayes' theorem. But now let's go to the coding part. Right, before we start you have to install two important binaries, and that's what we will doing first. So here in my terminal I write kgo install, and then the first package is a basic HTTP server. We will use it locally to test our website. So we have to serve a website to test our browser application, right? And the second command, I can just inject it with 2 ampersands in the PowerShell, is for installing WASM pack. Oops. And WASM pack is workhorse. It is really responsible to get this code of Rust into WebAssembly so that browsers can use it. And when I hit return, it is quite fast. In your case, it will take some time. But in the meantime, we will hop to our project file, the cargo terminal. And well, we see that there has been an update out for the ODE server. We will just neglect this at this point, because what we want to do, we want to have a new target, which is a library, and it has a special type. It's a so-called cdylib, and this is like a dynamic library that will be like used to wire it with the WebAssembly. So now we get an error. What is it? So we're missing a file. Like here, see, always a file is specified. We will go with a standard file, which is just lib.rs. And as soon as it is there, we shouldn't have any errors anymore. But what we need next are dependencies. And I will just copy paste those dependencies shortly and then explain them to you. So these are 4 dependencies. The first one, WASM bindgen. We will use it to mark types in Rust to be accessible on the browser side in JavaScript, because JavaScript is a language used inside the browser to do all the scripting, and we will do a bit of JavaScript too today. Then there is realloc, which is like a memory allocator. That means it is responsible to somehow get memory for use into our Rust program, and we need a special allocator for WebAssembly because it's different in the browser, okay? Then there's a crate called console error panic hook. We will just use it, as the name says, to hook up a console with all the panics that may occur in our Rust code, to have like outputs in the browser about those errors. And yeah, plotter canvas is just a sub crate of plotters and allows us to render into HTML canvas so that we can show it in the browser. However, next, let's see what we want to do. Like, we want to map the JavaScript console methods in the Rust scope, and we want to implement a macro for console output, and we want to end panicking. And all we want to do this in the browser, right? So for this, we will now hop back to the librs file and start to add a bit of code there. So first of all, we were talking about this global allocator, or this allocator. We will just change it globally and we'll use this we alloc, and there is a function which, or a variable which is just init. Okay, so that ensures that we are using the right memory model. Next, we want to use WASM bindgen, which is a macro, and this allows us to, in this case, we will just bring in JavaScript methods into the Rust side. Oops, it's extern, nicht export, because we want to import from an external source, right? And yeah, so here we have some function called log, and it is working on a string. We know this from the documentation of JavaScript, let's say. And for this, we use a namespace in JavaScript called console. Okay, that makes nothing else than like wiring this part with Rust. So a JavaScript function now accessible in Rust. The next thing is like I will copy this. It is a macro, and you can define macros in Rust, and it has let's say nice syntax, because here on the left side you have a matching of patterns, and we will just take any tokens inside this console log. So if you open the parentheses, then you write anything, and everything what is written, it is just forwarded to the log methods and given into the format args method. So that is quite powerful to come up with shorter versions of code. You may have a look into it for your own research. And what we want to do in the end is we want to have, like, I will copy this, two functions here. The first is just our panic hook. And let's call it hook panic handler. And there we use a panic set hook, which is a function from stud, I guess. And create a new box. Box is like a placeholder or like a variable on the heap. Like we can put stuff in there, and we will use console error panic hook is right, and then hook, which is a function pointer. Okay, we will use this function, which is from this external package. And then we want to have our own test method that is responsible to, as you may mention, log into the JavaScript console. Hello, JavaScript, let num 2. And now we just end it with our own macro, right? Yeah, and that's it from the Rust part. Now we get talking about how we get everything in a browser running. For this, we will now add a new World Wide Web folder. And there we will add 3 files, and an HTML file and 2 JavaScript files. One is Bootstrap, which is like the counterpart for the Rust code we wrote. It makes the Rust part like known to the JavaScript. And we have an index.js where we'll put our own JavaScript code to hook up the events of the browser, like a change or a resize and so on, or a mouse move. Okay, but first things first. we'll start with the index HTML. I will simply copy a HTML file here, and that's what HTML looks like. It's the so-called markup language, and here you have like a head. You can have some meta information like what is encoding. You can have a title of the entire thing. Then you have a body. You can say what happens when there's no script. We want to inform the user that that's not working. And we can include scripts like the bootstrap JS. And here is just a header. And the nice part is like you can actually open this up in a browser. And you can see here. And it's just a website, right? And here are some, in the headers, there are some links to interesting, helpful resources. So check that out too. But the more exciting part is a bootstrap JavaScript file. And there we have this code, which is just an init function. And what it does is like it saves variables, our hook panic handler, our test method, and we uses an asynchronous function to import JavaScript files. And as you can see, this package, Haber-Bosch JS, we don't have it yet. And as soon as init is done, we will hook up our panic handler and call the test method. So for this to be useful, we need a web server that provides this JavaScript. Okay. So what I will do now is I use WASM -pack build -- target. Oh, that's a quill sign. And we build for the web. Okay. So it's quite fast at my side because I did it before. What we can do now is we can fire up a basic HTTP server. Watch out, you have to be in the Haber-Bosch folder for this. And then we can access this website here. And you see, okay, it's not found. And that's because we decided to put it in this www folder. If I open it, we don't see a difference, right? Not yet. But if I press F12, which opens like developer tools in a browser, we have here console. And here you can see our hello JavaScript 42 and a panic. I added a panic in between the clips. So there's a panic. That's so exciting. And that's the reason why we're panicking, right? Yeah. But maybe shortly you get information here where the panic occurred. It's on the libls. So we can just hop to this file and see, okay, yeah, there's where this panic fired by me. Okay, next we will add our rendering into the browser. We start again on the Rust side. I just copy-paste what is needed, and here are some imports. We have a new struct for a point because we want to output where the mouse is in the canvas. Then we also use WASM bindgen on these types to make them accessible in JavaScript. Then we have a struct, it's called WebShard. This struct is very important for our canvas. It does the actual rendering and it has a convert function. So what you see here is like a pointer to a function that is capable to convert pixel coordinates in like points on this canvas. And well, here for both the type and for the methods, we need a WASM bindgen. And well, if you watch the first videos, you know we have like a good builder pattern to create a reactor. So here we just create a reactor with a specific pressure and catalyst, and then add 2 beds to it and generate an instance. And we use this instance for simulation and return it. So the magic actually happens in this function. So this will be called from JavaScript, and it has like an ID for the canvas in the HTML, which is a string. The catalyst will be given as a string because we don't make our animation yet known to JavaScript, and the pressure will be given as a number. and we will return either the web shard object or a JavaScript value with some error method. And first of all, we use console log to inform or to log about what is happening. We select then the right catalyst over the string, do the simulation, and with the result of the simulation, we can call draw concentration for canvas, which is very similar to the method we just implemented, and you find it in Web Visualization RS. And well, there are two differences in the method. First, it returns this map chord function that is responsible to map those pixel values into the coordinate system of the canvas. And internally, it generates a canvas, an HTML canvas instead of the PNG. All right, that's it from the Rust side. Let's wear our web developer hat again. So, next step, we go into the index HTML file and extend it a bit, because we still need the canvas to be in our website, right? And for this, we will add 3 new elements. I will copy paste them shortly. And they are a status bar, which says loading WebAssembly at the beginning, our coordinates for the mouse cursor, and the actual canvas element. All right. So next, we will hop into the JavaScript code to get this elements here, because the ID, this ID here, we can use it to access the HTML elements in JavaScript. For this, we use the global variable document and the method getElementById. All right, so now we can access these things. We also need an entry point, and that is the main function. But let's just say we want to update the inner text when WebAssembly is loaded in the main function. And maybe for you to see, I already added like JavaScript functions here, like main and setup. These are JavaScript functions that we can use here to. So we will just call main now, and setup it will be added later. So what we now want to do is to build with WASM, and as you can see, there's an error. Let's check for it shortly. Okay, no function associated with the apt new found for plotters prelude bitmap mag. Wait, why do we have the error? It's from the visualization RS, and you remember we have a new one, right? It's like the methods were like slightly adapted. The thing is, the bitmap backend uses a file system, and we're not allowed to use a file system in a browser because the browser is like a sandbox and we are quite secure there. And what we need to do here is like, what's the easiest option to do is, I think it was like config, we want not, and then tag it architecture is equal to WASM 32. Let's see what happens. Still an error. Ah, that's another function, right? I see the mistake. There were 2 mistakes, and we need to use this too. Let's see. WASM perk build. Yeah, we now get a lot of warnings because I had to add all the modules here, right? And that's are not used yet warnings, so we just neglect them or ignore them. Okay, we did pack it. Now we can fire up on the web server and open the URL. We have to go for www, and you see it's okay, loading WebAssembly, mouse cursor and plot. Why is it still loading WebAssembly? That check. Ah, yeah, we panicked. We panicked before, we have to get rid of the panic. Where was it? I think somewhere here. I see it. I get rid of it. So now we have to pack again, start the web server again. And there are tools to like simplify that. They will do this automatically for you. Trunk, for example. And now we get the WebAssembly loaded, and we're not doing anything with the other stuff yet. The next step is we want to get the plotting into our website here. So let chart be null, which is like it's not there yet. Then we want to have the setup canvas function, and we, besides that, need also a setup function for a class. So what we need here is we have a class webchart, and we want to have this JavaScript chart, web chart representing our web chart from WASM, right? So that means we need to have a look at the bootstrap.js and add sync web chart here. And we also need to call setup. Okay. So now, after we have the web chart in our let's implement a setup canvas function, but well, we start with update plot first. So we just leave this setup canvas function empty for now, and in the plot we start with having an inner text, because we are now simulating and rendering Haber-Bosch, right? And then, well, I will copy paste something here. So then we will set the chart to null, because it may be not null all the time when this is called. We start a performance counter. We set the pressure to 100. We set the catalyst to Fn. And then we call this draw concentration balances. Give it the ID of the canvas and the catalyst and the pressure. We then store a time point again in end, and let me fastly copy that. Then we update the status text. So this is a code that should work for us here. So now we just change JavaScript. That means normally this one should now work. And it does very well. Okay, so now we're ready to go. We have like the rendering done. It's taking a while because it's initializing too, right? And we need to now extend the tool. Like now we can add the functions that give really some interaction, like acting on events. If you can imagine, like if I would like change the size of this window, maybe something should change. And we also have this mouse cursor in plot, which is not working yet. That's what we will be doing next. So let's jump into the code. First we need a setup UI function, and there we will use a global variable which is window, add an event listener for resize, and every time we resize we just call setup canvas, which is not yet implemented. And we have another event listener on the window which is mouse move. Oops, forgot quotes. And yeah, let's call this thing mouse move. And let's also ensure that we call it in our main function. So we start with the first initial setup canvas and then set up the UI. Okay, so setup canvas, I will copy the remaining function. It is like a size calculation. What we do here is like we get the pixel ratio, which may be 1. And yeah, what we then calculate is the aspect ratio. Then we set the side depending on the width, 60% of the width, and we calculate then the width will be the size we calculated in pixel, and the height is the size divided by aspect ratio in pixel. Okay, and normally when I now update it, here you see this setup canvas, it's doing something, right? All right, next is our onMouseMove method, and let's get it into scope. Okay, and this method, it checks if this chart is there, and we start with mouse pointer is out of range, but here we have a argument to the message. It's an event data structure, and that contains the target. And if the target is a canvas, we know, okay, we're on the right thing. We will calculate the pixels, and then we call this chord function of the chart that maps the pixels. We give it into the local system of the canvas, and we then update the inner text. Okay, let's check. And it's not working yet. Why not? onMouseMove. I think here's a typo. E is missing. Let's give it again a try. Yeah, and you can see here it's out of range, and if I go here I can see where I'm pointing in the diagram. All right, next let's get some formulas in here to have more fun because we want to change things, right? So for this we will start by editing the HTML file. I just copy pasted here some code. We'll go through it immediately. So we have a element with a label for catalyst and a select, which has two options, and that's it. And the second part is a pressure, and it is a range from 180 to 202. It's 200 at the beginning, and we have a span here, pressure out 200 with an ID, and we use bar here. Okay, so we have some new IDs we need to map in JavaScript. But let's just firstly look how it looks like. That's what it looked like. Okay, it's not doing anything yet because we need to add JavaScript for that. So what we do is first we use some globals to map out these variables, and then we adapt our setup UI function with two new event listenings, and we listen on the change event of catalyst, which just updates the plot. But we also have a new function, it's called onPressureChange. Oops, miswritten. And well, this function, it's quite easy. So we have pressure out, we have an inner text on pressure out, and this is pressure.value, I guess. Oopsie. It should be pressure.value. And after that, we also update the plot, right? So with these changes, we should see something when we now change here. But it's not yet working. Okay, why isn't it working? I just remembered we had like an update plot, we're using constants. So it probably has been called, but here we need pressure value, but as a number. And this one is a bit more complicated. It's catalyst selected options 0.value, if I recall correctly. Now it's still, yeah, should be good. Give it a try. Okay, so we change. It's hard to see, but you can see it when you look at the length indicator at the bottom, right? Because it's redrawing in the full thing. And we can also change the catalyst. It's working. So, and as you can see, like in the meantime, we have just like this 6 milliseconds for simulating and rendering, which is quite fast, I guess. Okay, let's rethink. Isn't that like amazing? Like we end now with the coding part with this nice starting point here, where you can just render the diagram in the browser and change some values. And that is really a good starting point to continue. You find more code on the GitHub, and in this code you can access, or you see how the full version of the tool that you can find on this URL here is implemented. And that was what we actually were using in the video. And like really rethink that in approximately 2 hours, 2.5 hours, you learned how to simulate a Haber-Bosch reaction with Rust using an ODE server. That was the first video. The second video, you learned more complex topics like how to write your own iterator to provide data for the plotter crate, right? So we did this plotting and also the transformation of the data in this third video. We ended up being capable of saving PNG files onto our hard drive. But like now we really close the circle. Like we end up with a tool that is running in the web. You can just access it from everywhere. You can re-render quite fast. It's like around 5 milliseconds here. And like that's really cool. Because I think from the Rust perspective, most people think, okay, that's another system programming language, like in hard competition with C++. What is true? It's just better than C++. If you start a new project, just go the Rust route if you can, if there's not too much legacy C code or things like that. But what people are not aware of, it's really very well integrated in new web technologies like WebAssembly. And when you bring these two worlds together, you have like the web technologies for really great user interfaces, and you have the power and the control of Rust that allows you to do really very performance critical things like simulations. And by design, it just gets rid of a lot of security related bugs because you cannot write them simply in Rust. And yeah, well, I think 2.5 hours, it's dense content. I understand that there's not enough time to digest everything. And we also added, like with Jonathan, all the knowledge about the Haber-Bosch process, how the reaction works, how like the complete synthesis loop looks like. So there's a lot of knowledge, very dense in 2.5 hour videos. But now when you watched it, I really invite you to go to the references, learn more Rust, go to GitHub, play around with the code, and yeah, if you have some cool ideas, share them with us. And if you have any questions, feel free to ask. And before I now start to give a talk in this video, I would propose let us join Jonathan now. Jonathan, that wraps up our video series where we delved into the Haber-Bosch process, modeling, simulating and analyzing it through Rust implementations.
Tim, thank you very much for having me in this video series. I really enjoyed the experience and I'm looking forward to joining in future series.
I really enjoyed it as well. And that being said, don't forget to subscribe to the channel for updates on upcoming videos. You can find all the code on GitHub. And if you have any questions, please leave a comment. We're always ready to assist.
And if you found this video series informative and useful, we really appreciate your recommendation.
And we're excited for you to join us next time. Until then, goodbye.